not have our midterm during the scheduled slot. We will have it later, and I will give you the details. As I said, the midterm will definitely have an oral component. Whether we have a written component or not, I do not know yet. But even if we have a fully oral component, I will tell you in advance exactly what what I'm going to be asking questions on. In particular, everything that I've asked you to do in class, all the questions that I've asked you to work out in class, you must know all of that. That's a basic thing. Okay, so I have met most of you, but I think about 5+ people I have not met from class. So if you have not met me, then you should see me you should meet me in office hours tomorrow, right? Which will be at the usual class time. Okay. So our brief today is to do the chain rule first and then move on. Before we begin, are there any questions? Okay, good. So let's get started. And I'm going to do something slightly less pedagogical, is that I'm going to simply introduce the operator norm, because that is something that we will need in the course of the chain value, the chain rule. So usually I like to introduce a concept only when the need for that arises. But here, to be efficient, let's first just get this out of the way. So operator norm. Yeah, so let me also just start recording.
Recording in progress.
Okay, so let's just set the scene first. Suppose I have V and W that are vector spaces. Mostly they will be finite dimensional for us. Then, if I take all the linear operators from V to W, set of linear operators or linear maps, let's say, itself is a vector space. What are the vector space operations on this? How do I add maps and how do I scale a map? Come on, this is easy.
Pointwise.
So vector space via, let us say A plus B of V is AV plus BV, and lambda A applied to V is lambda times V. Okay. So it's natural to wonder, can I put a norm on this? And we will do so in the finite dimensional situation. So so let us say these are finite dimensional vector spaces, Rm and Rn. Then the dimension of L, Rm, Rn. What is the dimension?
Mn
Times n. And in fact, we can identify and we can identify L or M or N with the space of n by m matrices. And under this identification, again, the vector space operations, addition and scalar multiplication, they are the usual slot-wise addition of matrices and scaling everything in the matrix by the given scalar. So all of this, I hope, is completely, completely in your head now. So the question is, can I have a norm on this vector space? And the answer is yes. There are lots and lots of norms. This is a vector space, finite dimensional vector space. And I know that there are lots of norms on this. So we have seen the p norms with p equal to 1, 2, and infinity, but there are lots and lots of such norms. But we want a specific kind of norm here, uh, which will turn out to be useful, that is related to the fact that uh, that the elements of this vector space are not just a bunch of numbers, but they are functions. So we'll define the operator norm as follows. So operator norm, and maybe if you want to remember that this is the space of L, maybe L, let's say VW. If you want to remember that this is an operator from V to W, then we can write this. But mostly we will just write. So this is the supremum of the images of A, the images of vectors X under A, where the norm of X is 1. So there are various things to say. First of all, in order for this to make sense, you have to have norms on V and W. So remarks. The definition depends on the chosen norms V and W. But then there are a couple of other obvious questions. So what are they? Okay, so I mean, I'll just state them because this is all basic stuff. One is that I'm taking supremum of certain real numbers. It had better exist as a finite real numbers. Otherwise, this function is not a function. So why does this exist? So this is remark 0, remark 1. Why? Well defined. So why is this well defined?
Because A is
Right, because A is okay. So let's take a look at the definition. What are we saying? So so this depends on the norms on V and W, but let's picture just the Euclidean norm or the one norm or the infinity norm, doesn't matter. So
Right.
I'm taking supremum over what? I'm taking all vectors of unit length. Right? So you picture a sphere, and now I'm applying A to every one of those vectors and seeing what vectors I get in the target. So I will get some kind of bunch of vectors, and I'm taking the lengths of all of them, and I'm taking the supremum over that. Why is this supremum not infinity? That's the question, right?
Because A is continuous.
Right. So both of those things that you just said. So one being a linear map, A is continuous. And we know that the set of which I'm taking the image is a compact set. Why is it compact?
because it is closed and bounded.
Because it is closed and bounded. So Heine-Borel is really required over here. Okay. So why is it well defined? So let's say X such that the norm of X is equal to 1 is closed and bounded in B, therefore compact. By the way, so it is bounded, but why is it closed? Come on, so this should be basic now. Why is the set that I have written
Mod
closed?
x equal to 1 domain is closed.
Because the norm is continuous.
Norm is continuous, and moreover, I mean, norm is continuous sort of by definition, you see, because I mean, limits I'm using with limits I'm defining with respect to the norm. So there is nothing much to that. But why is it closed? What is
singleton is closed and then inverse of it is closed.
right? So you see, this is inverse image of a single point, namely the number one, the number one on the real line. That's a closed set. Its complement is open, right? I can put a small open interval around everything in the complement. So this is an inverse image of a singleton set, which is closed. And since this is a continuous, the norm is a continuous function, therefore the set is closed. And it is bounded, therefore it is compact. Now what? Therefore compact in V, A being linear, is continuous. So let's call this set something. So let's call this set, I don't know what, S. Therefore, A of S is also compact. So what? Is a compact subset of W. And I'm going to say VW finite dimensional. Otherwise, we are in difficulty. Yeah. So what if this is a compact subset?
It is closed and bounded.
Right. So this is bounded. And therefore, I can take the supremum. Will this supremum be achieved?
Yes, sir.
Right. So this is yet another thing, right? On a compact set, if I have a continuous function, then it attains, it has a largest and a smallest. AS is bounded. Okay, so this is the first thing. But what is the next obvious thing to check? Well, I have defined a function and I have said that it's a norm. So I have to check that this really satisfies the conditions of a norm, right? So what is there to check? Need to check that this is a norm. So what is there to check?
So it's pretty clear that it's positive, like that this is non-negative, and that the constants, like factors, like when you multiply the argument by constant factor, that gets taken out, right? But now we need to check now is the triangle inequality.
Okay, so so let's see this. So what we are saying, is that norm of A is greater than or equal to 0, and norm of A is equal to 0 if and only if A is equal to 0. Is that clear? You see, the norm is a supremum of norms, and those vectors themselves are going to be non-negative. So if I take supremum of non-negative numbers, it's going to be non-negative. And when will a supremum of non-negative numbers be 0? Precisely when all numbers are 0. Now, all numbers are all AX such that X ranges over this unit ball are going to be 0. That means I can pick a basis and just scale each one of the basis vectors to a unit vector. And A of each one of the unit vectors will then have to be 0 if the norm of A is 0. But that means by taking linear combinations, A of everything has to be 0 because A is a linear operator. Okay, so that was one thing. Then lambda times A, the norm of that is norm of lambda times the norm. Is this okay? So I'm just going to say check mark over here. So is this difficult? How do you check this? Well, this just follows from the fact that scalar multiplying an operator by a scalar is just pointwise. No? So if I try to take the norm of 2 times a, that means I have to apply the operator 2 times a to each one of the unit vectors. Take the norms and take the supremum. But 2 times a applied to a unit vector is just the same as 2 times a applied to that unit vector. So everything is just going to get, I mean, the supremum now is going to be whatever I was taking supremum of, whichever numbers I was taking supremum of for a. Now I'm just going to take the supremum of 2 times those numbers. So of course it will get multiplied by 2. And in general, it will get multiplied by the absolute value of lambda. So this is straightforward. How about triangle inequality? So norm of a plus b.
Just the way we have defined the sum of linear maps, from that it will
Exactly.
directly follow.
Because you see, what I have to do is that on the left and the right hand side, in order to calculate those, I have to apply those to any. So because a plus b of applied to any vector x is just ax plus bx. And so if I take the norms, then yeah, sorry. So what is the issue over here? Where is the inequality going to come from? And
So the sum of the supremums will be an upper bound for the set
exactly.
norm
So,
of a plus b.
yeah, so the point is, if I now take the and here is the thing. If I take the norm of ax plus bx, then of course that is going to be less than the norm of ax plus norm of bx. And now I take supremum and etc. So it will do the job. So this is easy. I'm just going to say this is easy. Okay. So some basic properties of this. So I'm going to basic properties. And really the first one so I claim that norm of a times a vector b.
So,
Yes.
this norm of ax plus bx is less than equal to norm of ax plus norm of bx.
Right.
How does this follow not from the triangle inequality? Or this is norm on v.
Right, exactly.
W,
Or rather, this is okay. So let's just say so by or not by. This is true where not in v because I have applied v.
Yes, it's a norm on w.
So this is true in w. That's where this is true. But one thing I should say, we've said this many times. You see, the definition of the operator norm depends on the norms that I have chosen on V and on W. But if V and W are finite dimensional, then the notion of continuity or limits, all of those notions are going to be independent of the norm that I put on this space of linear operators. Because it's a finite dimensional space. Its dimension is dimension of V times dimension of W. So this norm is going to be useful for us, but the topology does not really depend on which norm I. Okay, so basic properties. So this is what I have. And the way to do this is fairly easy.
So what is the map AV?
Okay.
Oh, it's okay. So AV was just all right.
Right. So remember, A is a linear operator. So it's AV is just A applied.
Right. So when we take the norm of AV, we just take the norm over the vector space, and when we take the norm of AV, this is the operator norm.
Right. So you see, it's a bit unfortunate. No, I'm just using norms, but in this claim, the three norms that I have chosen, they're all three in different places.
Yeah.
Right. So on the left hand side, okay. So let's just write a subscript over here to understand what's going on. So this norm is in this norm is in W, and on the right hand side, when I take this A, that is the operator norm, that is in L, and the norm of small v, that is in the vector space. Okay, so we have to keep the meaning a little straight over here. But anyway, so how do we do this? The idea is quite simple. You see, in order to calculate the operator norm, I'm looking at unit vectors only. But all the other vectors are really obtainable from unit vectors, right? Just by scaling by the length. So this is quite easy. So of course, this works only for if v is equal to 0. Then there is nothing to prove here, right? Because on both sides I'm taking, I mean, there is a slight amount. If v is equal to 0, then on the right hand side I have 0. But on the left hand side also I have 0 because A is a linear map. So A of 0 is again 0. Just excuse me for a moment. Okay, so what do I do in general? If v is not 0, then I just let u equal to v divided by norm of v. So my u's and v's are, and of course notice that norm of u is equal to 1. So what gives now? So I know that the norm of A is greater than or equal to norm of A applied to u, because norm of A is the supremum of all of these things. You see, this idea of operator norm is really very simple. Basically, you are taking the unit ball. Pretend for a moment that this matrix A is diagonalizable. Okay. Then what's happening is that choose an eigenbasis. What is going to happen is that each one of the eigenvectors is going to get scaled by something, right? So this nice sphere, when I map it by means of this linear map, it is in some directions it is going to elongate, in some directions it is going to shrink, in each one of these characteristic directions. And along all other directions, it is going to be some kind of linear combination. So this nice sphere will get elongated, squished, and something or the other will happen. Yeah. Nonetheless, it is going to be a closed and bounded set. It's going to be a compact set. So what this operator norm is saying is that I start with all the unit vectors, and there may be some, elongating and compressing, etc. But nonetheless, whatever shape I get by applying this map, what is the vector that is the farthest out vector? Right? And this is a reasonable way to think of this. And somehow what we are saying is that, look, if I apply this A to vectors of large length, then I am going to get vectors of large length. The point though is that the scaling that occurs, the factor by which you get scaled, that is going to have a supremum. And that's exactly what this operator norm is capturing. Okay, so this norm of A is greater than or equal to norm of A applied to U, where I have taken a specific unit vector. So now run with this. What happens? So what is that? That is really just the norm of A times A applied to V by norm of V. Okay, it's looks a little complicated, but it's all very simple, right? See, A is applied to that vector. A is a linear operator. So norm of V, that thing in the denominator just comes out of A. And then it also comes out of the norm, no? Because the norm is a homogeneous function. So what is this equal to? This is precisely equal to the norm of AV divided by norm of V. By linearity of A and by the norm property. But that's exactly what we want. Just put norm of V on the other side. So any questions so far? Okay, so see what this is saying. The property is saying is that when I apply A to a vector, then that vector can get, then the magnitude by which the vector gets scaled is bounded. And the bound is the norm of V. Okay, so number 2, which is really a sort of formalization, just saying this in other words. So AX, or let's say V. EV. Suppose M is a factor that works for all V, implies what should be the connection between the norm of A and the scalar M, the constant M?
Less than or equal to.
And in fact, more is true. Suppose I take all such scalars that M such that AV, norm of AV is less than or equal to norm M times norm of V for all V. Okay, so maybe, yeah, okay. Then what will the norm of A be related to? So we know that everything in the set that I have written over here, let me put it on the opposite side. So what I have shown is that, or not shown, but what we have stated is that norm of A is less than everything in this set. So in fact, the norm of A is less than or equal to the infimum of this set. But in fact, this is precisely equal to the infimum. And okay, so let's just do this a little bit. So the first part is very easy. So let's just say, suppose AV so why is the norm of A less than or equal to M? This is straightforward. This is true for all V, correct? So in particular, yeah, so can you complete the argument? This is easy. How do I calculate the norm of A? To calculate, yeah, so I apply it to the unit vectors, right? So, but what happens for unit vectors? In particular, for all V with norm V equal to 1. So what happens? So norm of A V for is less than or equal to M. And therefore, if I take the supremum of all of such things, the supremum will also be less than, etc. So there is nothing to this. The rest of this is just a simple exercise. See, what do I have to do? So the first part already tells you that the norm of A, we already said this, that the norm of A is less than or equal to the infimum of this set, because norm of A is less than or equal to every such element. So why is it the infimum? Well, that just means you have to show what? That if I take a number that is less than the infimum of the set on the right hand side, if L is less than infimum of the set, then what should happen?
It should no longer lower bound the set.
Exactly. So that means that there has to be a vector V, a unit vector U, such that A times U has to be strictly then show that there exists U of norm 1 with sorry, what? I've almost written the proof, but so what? Just help me here. With norm of AU greater than F, etc. Okay, good. So this is fine. Any questions so far? Really, it is the first property that is going to be enough for us in the proof of chain rule. But now that we are doing this, let us say a few things. So you see, one thing that I can do with linear maps or with maps is that I can compose them. So it is very natural to consider what happens to norms when I compose operators. So let's write this down. So suppose I have U to V to W vector spaces, and I have operators A and B, finite dimensional vector spaces, right? Linear maps between finite dimensional vector spaces. So using this, using the intuition that we have, so if I compose A and B, remember I have to then write this B followed by A. Can you think of any kind of connection between these three quantities? Think intuitively.
Maximum.
Okay, so let's just follow our nose and see what happens. Okay.
No, sir. Multiplication.
Yeah. So let's just. So how do I calculate the norm of an operator? The operator that I want to start with is the composition. That is the one that I have, right? So let U be any unit vector, or let's write it like this. Take U with norm. Sorry, this U is in the source vector space, right? And it has norm 1. So what I have to do is I have to calculate this, no? And I have to calculate it for all of them. Okay. So what gives now with this?
We can say it's less than or equal to norm of B multiplied by norm of A times B.
Correct, exactly. So this this is just completely dumb, but BA applied to U is really just same thing as B applied to A, correct? Yes, that's what the meaning is. But now I know, thanks to this property number 1, that see, U is a unit vector, but AU need not be a unit vector. In fact, that's so the whole thing, no? The operator norm is somehow supposed to capture how much you can lengthen or shorten, as the case may be. But I know that this is really less than or equal to the norm of B times the norm of E. But what do I know about AU? Well, I mean, I have taken a unit vector, so AU is real. So this is really the less than or equal to the norm of B times norm of A. Because you see that AU, it's the image of a particular unit vector, right? So of course the operator norm is the supremum of the length of all of such things. So it's going to be less than or equal. Now notice, now take supremum over. So what is this? What we have seen is that, so let's write this carefully. So this is less than or equal to, and it's really just the product. So this is a useful little thing. By the way, so a remark maybe. Remark. So you see the map that takes A comma B to BA. This is a map from where to where? Okay, so let me write this. On the
Domain
right
of
hand
A
side,
to range of B.
it's the linear map from U to W, correct? On the left hand side, what do I have? I have linear maps from U to V. That is what A is from. And linear maps from V to W. And I can write this as cross. But I want to think of this as a vector space, you see. This, the set of all ordered pairs of vectors from one vector space and vector from another vector space. That's also a vector space under slot-wise operations. That's the direct sum. So let me write this as direct sum. Is this okay? You must have seen this in linear algebra, right? In particular, R2 can be thought of as R direct sum R. That's how we do it. So this is a composition or multiplication map. Multiplication of maps. So this is continuous. Why is this continuous? So the exercise here is going to do this using operator norms. But there is a very basic reason why this is continuous. So in order to check continuity, I can use any norm I like. No? So identify these spaces with matrices. So if the dimensions of U, V, and W are, let's say, K, L, and M, then I have a map from what dimensional vector space to what dimensional vector space? Okay, so is this difficult? I hope not. What is the dimension of LUV? It's K times L, or whatever, the product of those two dimensions. That of V and W, that of LVW is LM. So what is the dimension of the direct sum?
Product.
No. What is the
Sum. Okay, sorry. Sum.
So the dimension of the direct sum of two vector spaces is just whatever is the dimension in the first slot plus whatever is the dimension in the second slot. And likewise, the right hand side will have dimension product of two of those numbers. So it is KL plus LM to KM. Whatever be the case, it doesn't matter. It's just a couple of numbers, right? Think of A and B as matrices. What are entries of BA? How are they obtained? The matrix of BA.
They're all polynomial functions of the entries of A and B, in
Exactly.
particular linear ones.
Exactly, right? So you see all these sort of little basic rules that we built around continuous functions, this just gives it to us. There is nothing to this. The entries of B and A are obtained by taking some individual entries of A, individual entries of B, and then multiplying them and adding them. But all of these operations are continuous. I mean, if you want to do this formally, then you should say, well, I'm taking the projection onto certain coordinate. Then I'm taking the product of such projection maps. Then I'm taking the sum of those projection maps. That is going to give me one coordinate of this BA. But a map to R to the whatever is continuous if each one of the component, if each one of the real valued maps that gives me each slot entry, that is continuous. We saw this early on, right? So all I have to do is each one of the slots of the matrix is continuous, and that is obtained by projecting and then adding and multiplying. But you can also try to do this using the operator norm if you want. So is continuous. Because each slot, for example, because each slot of the matrix BA is obtained by adding and multiplying entries of A and B, or rather multiplying suitable entries of A with suitable entries of B and then adding. So I've written it a little sloppy. Maybe I'll say adding and multiplying. But you can also try to do this exercise. So exercise, show if AN goes to A, BN goes to B, LUV And do you see that in order to do this, okay, so a couple of comments. So one, in order to do this, the operator norm is going to be useful. Or norms are going to be useful, right? Because I'm taking sequences. And you see that what I have written over here, the claim, that is exactly what the continuity of this map is going to be. Right? Of course, what you have to do is you have to give a suitable norm on the direct sum of two vector spaces. So think about this as a, as a way to sort of get comfortable with motions. All right. So any questions so far? Let's get back to chain rule. So we did a bunch of scene setting yesterday. So let me just quickly write that down. So what is the statement? The statement is that U is an open set, open in Rm. From that, there is a map to Rn, which I call F. And then there is a map from a part of that to Rk. I want to calculate the derivative of F composed with G in terms of individual derivatives of F and G. In order for G to have a derivative at a certain point, G needs to have a neighborhood around that point where G is defined. So this is how we are going to set up. So V is an open set in R n, and G is defined on this entire open set. So this is what I have, and let us say that A under F goes to F of A, which I call B. So the statement is the following. Suppose I am given such a thing. And further, suppose F is differentiable at A and G is differentiable at B, which is at F of A. So all of this is given to us. Then what is the claim? That the composite F followed by G is differentiable at A, and it is, the derivative is given by the derivative of G times the derivative of A. Of course, the times really has to be understood properly. So everything has, so maybe I should really say this is circle, because it is, so F prime of A, so note what kind of animal is F prime of A? Come on, F prime of A is what kind of gadget? It's not a number.
Linear map.
It's a linear map from where to where.
Rn to Rn.
And G prime of F of A, which is the same thing as G prime of B, that is a linear map from Rn to Rk. So this is a composition of linear maps. So this is the statement. Right? Let's proof. Let's have our sort of scene setting. So recall the definition of a linear operator. So what I have is that limit as h approaches 0 of f of a plus h minus f of a divided by h is supposed to be the derivative, but in the multivariable case, the way to interpret it is that minus p of h divided by h. Of course, I have to take the norm. And I will take norm up there also in order to have just a limit as a real number is equal to 0, as is the limit as k approaches 0 of, sorry, not f, g of b plus h minus g of b minus, okay, so not h. I'm taking k to be a small vector in the middle vector space minus, okay, so s of k divided by k. So of course, what do I have over here? So where p is equal to f prime of a and s is the map, which is g prime of f of a, which is the same thing as g prime of b, because I have called b to be the point f of a. All right, so just a little bit of, so here is a, here is u, here is b, and here is b. And f really just maps. Okay. So remember we had these remainder terms. So I'm going to call let me follow what I had last. So just notation. So first just notation. So alpha of h is the term at the top, which is f of a plus h minus f of a minus 2h. And so I have that limit. So the limit up top really can be thought of as limit as h approaches 0 of the norm of alpha h over h is 0. So let me give also a name to the quantity which is, so I'm going to say epsilon of h is equal to alpha h divided by h. What do I know about this quantity? The limit of this quantity as h approaches 0 is 0, right? So so this approaches 0 as h approaches 0. And likewise, let's write down the quantity for the other one, g of b plus k minus g of b minus s of k. And I know that the ratio of this quantity with k, so eta of k, which is by definition beta of k divided by k, 0 as k approaches. Okay, very well. This quantity eta, is it defined for k equal to 0? The answer is no, because I have defined, because it has k in the denominator. So let me just change this slightly by saying that I define this to be equal to 0 for k equal to 0. So think of eta as a function. So eta is a function from where to where? So note, eta is a function from where to where? Look at the picture. This is A, this is B.
It's from V to real numbers.
Right. So it is not quite from V to real numbers because you see, this K is the offset from B that I'm taking.
Right. Yes. Yes.
Right.
Yes.
So you see, the values of K are going to form some kind of open set around 0. So this really is a function from the set V minus B to real numbers. Positive real numbers. I mean, non-negative real numbers. In fact. So what is V minus B? That is just take every point in V and just shift it by B. Because I'm thinking of these as small vectors. All right. So by the way, this is all just setting up the terminology, and please ensure that you understand the meaning correctly, because if you don't understand the meaning, then the proof will be, it will just make no sense. I'm trying to set up the terminology so that the proof becomes transparent. Okay. So, all right. What can I say about the function eta at 0?
Continuous.
It is continuous. That's the whole point of saying that the derivative of g at b is equal to, exists and is that linear operator S, right? So eta continuous at k equal to 0. Yes, go ahead, please.
Sorry, why did we take b minus b again? Could you explain?
Right, but you see, you just look at what I'm plugging into eta. I'm plugging into eta things that are k, right? So what is k? K is b plus something.
Okay.
Right? So see, just like when you take the derivative, you take limit of a limit of x plus h, f of x plus h minus f of x divided by h as h approaches 0, right? That's because I have taken h to be the increment. That is the point, right?
Okay.
Okay, so that's all. This is just a shift, nothing else. By the way, so what I have done about eta, I can do the same thing about epsilon also. There is no issue with that, but I won't need it. I could do that, but I won't need it. Okay. All right, so this is really just setting this. Now I'm going to do the following. I'm going to take, see, what do I need to? So want. What is it that I want to show? See, I want to show that the derivative is the composition of the two linear operators t and s, right? So this is t and this is s. So what I need to show is that the limit as h approaches 0 of what? F composed with g of a plus h minus f composed with g of a minus what? Come on.
SPH.
S of t of h.
S of t of h. All of that divided by h. Of course, I take the norm. And this is equal to 0, right? So it is good to consider the quantity on the numerator. Yeah. All right. So what I'm going to do is the following. You see, I am going to, so what is going to require is that I need to bound this quantity. The quantity that whose limit is supposed to go to 0, I should bound this quantity in terms of individual operators s and t. What is happening individually with functions f and g, and then the respective derivatives s and t, and show that that upper bound itself goes to 0, so that something smaller than it will also go to 0. Right? For this, what I'm going to do is the following.
Sir, is it G of S?
Sorry, say that again, please.
Sir, is it G of S? You can F of G.
Sorry, say that again. I didn't understand. G of what?
Isn't it G of F instead of F of G?
Oh, sorry. Yes, absolutely right. We pay this price for writing functions on the left. What happens first and what you write first is G. Thank you. So which is limit as h approaches 0 of, oops. Okay, so I'm going to say, let's write the second thing as g of b minus SPH divided by h. Now the first term, you see, I have written g of b, right? So it would be nice to write this also as g of b plus something. And I want this to be k. So this is what I want. But what is the value of k? You see, I have replaced this f of a plus h by b plus k. That's what I've done, right? What is happening is very simple, okay? A moves by a little, so its f also moves by a little. A moves from A to H, so f of A moves from, so f of that moves from B to B plus something, right? I'm just calling that increment to be k. So k is going to be what? F of A plus H minus f of A. Which is equal to f of A plus H minus B. I have written three qualities there. They are all really saying exactly the same. If you recall yesterday last time when I wrote down the heuristic, there was delta X, delta Y, and delta Z, right? And I had to compare them. So the same thing is being done over here. All right. So very well. What do I do now? So let's take a look at the numerator over here. G of B plus K minus G of B. And now the second thing that is over here, S of P of H. You see, so I'm taking a specific value, right? So where K equal to, so we have taken value of K depending on H. So now maybe what I should do is I should draw a line over here. See, whatever I wrote here about K, that was for an arbitrarily taken K, and K was going to 0. Now K is depending on H, right? So now K is a function of H. What happens to K as H approaches 0?
It goes to 0.
It goes to 0, and the reason for that is, okay, just give me a moment. Yeah, so it's a continuous function and at 0, and as H goes to 0, K goes to 0, because I know that F itself is continuous, and the reason F is continuous is because
No, it's differentiable at A. So
right, and we showed that last time. Okay, so here is the idea. Now, what is TH? So let's take a look over here. You see, I have defined these notations alpha and beta, and then epsilon and eta about some error terms, right? So let us write that down in terms of, so what is TH? So I'm taking S of P of H. I know how to do something about this, this quantity G of B plus K minus G of B minus S of something. So I'm taking S of what? Let's write this down. G of B plus K minus SPH is equal to G of B plus K minus G of B minus S of PH. Now what is PH? P of H is F of A plus H minus F of A minus alpha H. So perhaps I should write this down. So TH F of A plus H minus F of A minus alpha of H. That's how alpha was defined. But what is F of A plus H minus F of A? That's how the function is incrementing when I'm incrementing, and that's exactly what I called K, which is K minus alpha H. So S of K minus alpha H. All right. So all right. So what can I do with this? S is a linear operator. So this is G of B plus K minus G of B minus SK minus S of alpha of H. This is begins to look nice, no? The reason why this begins to look nice is the form. I want to bound this g of b plus k minus g of b.
Sir, it should be plus S of alpha H.
S of alpha of h, right? So remember, S applied to alpha h is really okay. So I will write it down. But the same.
Yeah, I mean it should be plus. Yeah.
So this divided by h, norm of h, is the same as g of b plus k minus g of b minus s of k plus s of alpha of h, and all of that divided by h, norm of h. But you see, by triangle inequality, I can now separate. Okay, so the idea over here, what is happening is that now I have obtained two terms. Now the first term is something to do only with g, at least the numerator, right? And the second one seems to be more to do with, remember, alpha was the error term for just f. So somehow I am able to split both of them. So what I would like to do is estimate both of these separately. What gives now? Any ideas? Okay, let's look at the second term. If that s were not there, then what could you say about that term? Pretend s was just not there. Instead of s of alpha of h divided by the norm of h, it was just alpha of h divided by norm of h.
That goes to 0.
Then it goes to 0, right? So I'm in great shape over there. All right. But now I claim that the presence of s does not really affect us too much. And the reason for this, the magic words here are the operator norm. Just look up the operator norm. I'm taking s of alpha of h and taking the norm of that. What do I know about such a thing?
We can bound it by norm s times alpha h by h, like norm of.
So you see this idea that somehow the magnitude by which s is scaling things in different directions, that is all bounded above. And I can capture that in the operator norm that comes in very useful here. So want to bound each of these separately. So let's say the second term. So I know that s of alpha of h is less than or equal to the operator norm of s times the norm of alpha of h. And I just divide that by h. So let me just write it in this fashion. And now the operator norm of s is a positive, it's a finite number. So this goes to norm of s, operator norm of s times 0, which is equal to 0. So good, I'm happy. I'm done with the second term.
So couldn't we just do this by putting...
sorry, say that again, please.
Couldn't we just do this by putting the scalar h inside the upper norm and then inside s?
No, sorry, I'm not following. Say that again, please.
Couldn't we just do this by putting norm of h inside norm of s alpha h? Because it's a scalar. And then inside S because it's a linear map.
No, but you see, S is being applied to alpha of H, no? So I'm not really sure what I don't think I'm understanding what you're saying. Yeah, so maybe we can discuss this after class.
Yes, sir.
But I hope you see how the operator norm really helped us over here. Okay. Now the first term, bounding the first term, is a little more complicated. But even over there, the operator norm will help us. And this time, the operator norm of T will help us. So how to bound the first? And so we are out of time. Let me just, sketch this quickly. And if you want, I can do this again at the beginning of the next class. But the idea is the following. Okay. So you see that. So what is the first term? Remember, this was the term beta of k divided by. That's what we had. Remember, it's the error term. What I'm calling the error term. Beta of k is g of b plus k minus g of b minus sk. That's exactly what I have. So what I have is the ratio beta of k to h, not to k. Right? And I want to show that this goes to 0. So heuristically, what am I going to do over here?
Divide and multiply by k. Norm.
Right, divide and multiply by norm k. Now, really speaking, what will happen is that norm of k, see, sometimes h may be positive, but I mean, h may be a non-zero vector, but k may be 0. It may happen that f of a plus h and f of a are both the same. Right? So, but this is really not a serious problem. What you do is, instead of dividing, you do this multiplicative. And that is the reason why we introduce this function eta. So what do I have over here? Note that I always have beta of k is equal to eta of k times k. Of course, I have to put norms. Remember, eta is a real value function. So at the expense of this finite factor eta of k, I can replace beta of k by k. So this term, so what does this give me? I can replace beta of k by
Eta of k norm.
Eta of k, which is just a real number, which could be 0. But I'm happy if it is 0, right? Because I want to drive this term to 0. Times norm of k divided by norm of h. And you see, morally speaking, I'm done. Because what I know is that as h approaches 0, k approaches 0. So this is all going to work out okay, but I really have to bound this property. So there is one more bit of estimation to do. So let's estimate k. Estimate k. So how does this go? What was k? Let's again remember, I have taken a specific value of the value of k is so I want to do this in terms of t. Sorry, so so this is the equation that I want to have. T of h is k plus alpha. So I'm going to write So I'm going to write as ph plus alpha of h. Okay, so by taking norms, I get norm of k is less than or equal to the norm of ph plus the norm of alpha of h. And now this is proceeding beautifully. What do I know about the norm of h? Remember, I want to divide this thing by h, right? So working out beautifully, now? What can I say? What is norm of ph divided by norm of h? Do I have any kind of handle on that? What do I know about norm of th? Again, the magic word is operator norm. So norm of th is less than or equal to the operator norm of t, the maximum scaling factor, times the norm of h. Sorry, this is a bit. So what can I say about the first term? Norm of th is less than or equal to the operator norm of t times the norm of the vector h. So what do I know about the first term? This is less than or equal to
Operator norm of t.
the operator norm of t. And the second term is just alpha of h divided by h. That is perfectly good. I like that term because what do I know about that term? What happens to it as h goes to 0?
It goes to 0.
It goes to 0 because alpha of h was obtained as the error term for the derivative of f. So putting it all together, so this is less than or equal to, so all putting together beta of k, what do I know about that? So that is norm of, this eta of k times this. Remember, h is under my control. I'm going to take limits as h approaches 0. So I can arrange h to be non-zero. There is no issue. I know that this is eta of k times norm of t plus and finally victory. As h approaches 0, eta of k approaches okay. So let's look at the second term. The operator norm, so this is just approaches t plus 0, which is a finite real number. What about eta of k? Maybe I should write this down. Sorry, so 1 and 2. So as h approaches 0, I want to say that I want to see what happens to eta of k. Well, as h approaches 0, what happens? What does k approach? So as h approaches, right? Because remember, k is the difference between f of a plus h and f of a. F is a continuous function. So as h approaches 0, k is approaching 0. And therefore, eta of k also approaches 0 because eta is continuous at 0, you see. Remember what eta was? That was the whole point of defining that function eta. Sorry, where is it? Now, beta of k is eta of k times the norm of k. and that ratio is approaching 0, and I'm defining the function eta to be 0 at 0 at k equal to 0. Therefore, the function eta is continuous at k equal to 0. So if k approaches 0, eta of k also approaches 0. As a result, this entire right hand side is so this is approaching 0, this is approaching normal. So their product approaches 0. All right. So we really have to stop. But this proof is really not difficult. You have to get the idea of somehow using the operator norm. But once you have the operator norm, and it's kind of given that you should need to use triangle inequality. After that, it really is just a souped up version of the proof in the one variable situation. So let me write this down and stop. Perhaps change the color here. So you should be able to not because this proof itself is very important. Of course, the result is very important, but somehow the proof puts together many ideas that you have learned so far. Just like the proof that all the norms on a finite dimensional vector space are equivalent, that used a number of ideas together in a nice way. So similarly, this proof uses several ideas. Okay, so you should be able to teach this proof on your own, and in two ways, both top down and bottom up. That means that you should be able to give the big picture, that is, what is the heuristics. The heuristics is really not very different from what we saw yesterday. This small thing about ratios, delta z by delta x is delta z by delta y times delta y by delta x, and then using the continuity of the first function. So both the big picture idea and exactly how this big picture idea is translated down to the last detail. So both this top down and bottom up, both ways you should be able to explain this. So in terms of both big picture and down to the last detail, All right, so let's stop for today.
Recording stopped.
Yeah, I really apologize. I went way over. So what comes after this is that there are some standard things that we have to pick up. So one is the mean value theorem. We also have to see what it means to take the derivative of the derivative. So far we have derivative only at a single point. In order to have the derivative of the derivative, I have to regard the derivative as a function. So let me just say next. So one is, or even before that, derivative as a function. So characterization of C1 maps. Characterization in terms of partial derivatives. So mean value theorem. And well, next inverse and the inverse function here. And its cousin, the implicit function here. So this is where we are headed in the course of next several lectures. So I'm happy to now discuss any questions or anything that people may have. This proof, it may have seemed that this proof was just very complicated, but please try to realize for yourself that the proof is actually not difficult. You sort of follow your nose, and some key ideas you keep in mind, that you have to estimate. So what was the estimation? This was the main thing that we needed to estimate. So what I have written over here. This is the quantity we needed to estimate. So what was the idea? Breaking down this quantity into two parts, estimating each one separately. For each one, the operator norm was useful. And in one case, we had to use the continuity of f to show that when the value of a moves a little bit to a plus h, b also moves a little bit only from b to b plus k. So as h goes to 0, k goes to 0. So really there wasn't much more than this. But to put it together, required some kind of notational effort and just getting all your estimates right and triangle inequalities correct. But you should reach a state of mind where this does not seem like a big deal. Of course, writing down all the details may take some time to work out, but it should not feel difficult or that, oh, what was this proof about? Okay, so any questions?
So can you take the part where we proved that multiplication of operators are continuous with respect to the operator now?
Yes.
So can you explain that statement? I mean, what we are trying to prove in terms of epsilons and all that.
Okay, so you mean the exercise that I gave you, or what I said before, the proof in terms of, or the proof that I sketched earlier?
Yeah, the proof that you sketched earlier.
Okay, so let's write this down. I sort of need to go down over here, and let me give a small example. So let us take this map from R3 to R2, where x, y, z goes to x square plus y, z cube minus 3, whatever, and x, y, z. Is this map continuous?
Yes.
Okay, so how do we do that? This is, so if you agree with me that this map is continuous, then what we wrote over there for, so let's write this down for 2 by 2 matrices is continuous. So let us write this. Let us write down the map for L R2 to R2 cross L R2 to R2 to L. Okay, so you know what? Let's do something simple. Because this will just be okay. Might as well. So sorry.
Sir, I think I understood. So,
but anyway, I mean, let's write this down once, just so that there is no mystery over here, is what I wanted to tell. So L R2 to R3 and L R3 to R1, I will get a map from R2 to R. So let's write this down explicitly. So R2 to R3. So what kind of matrix will that have? How many rows and how many columns?
2 by 3.
Right. Right. So so remember, the map goes to R3.
3 by 3.
Right. So that means that every column vector has to be in the target. So, okay, so this is going to be A, B, C, D, E, F. Okay. And let us, so this is multiplication. And then I have from R3 to R1. So how do I write this? So this is going to be a single row. Yeah. And let's call it PQR. Of course, this matrix, if I call this A and this matrix is B, then the multiplication is really BA. Yes. Because I'm first doing A, I'm first doing the operator A, then doing the operator B. That means BA. So what is this matrix? It's very easy to write down, no? So R2 to R1. That means this is going to have
1 by
right, 1 row and 2 columns. And what are the numbers? You know, I mean, so whatever the details are, you see how it is going to work out. So what is the first number?
PA plus QB plus RC.
PA plus QB plus RC. And the next one is going to be the similar one, right? So the next one is what? So you see why this map is continuous, no? It's just made in terms of adding and, you know, multiplying slots and adding slots. If you want to be completely sort of pedantically accurate about this, then let's look at the map over here. So when is a map from something to Rn continuous? Precisely when the map in each slot, the real valued map in each slot is continuous, right? So if I want to show that a map to some matrix space is continuous, then all I have to show is that the real number in each matrix entry, that is a continuous function of however many variables you have. So you look at this map, for example, x square plus yz. How do I get that this map is continuous? Well, you say that this map R3 to so there are these 3 maps R, R, R. And I will call those maps pi1, pi2, pi3, which take x, y, z to x to y to z. And we said that these maps are continuous, right? So what is this? So what is this map to A? So that map is R3 to R, which is given by pi1 square plus pi2 pi3. And we said that so this is, let's be sort of painfully pedantic over here, because it's like, you know, if you're called upon to justify, you should be able to justify everything down to the last sign. So let's not even do this. So this is really what, sorry, just one second. So let's say that this map is R cross R. Sorry, one second. Help me over here. Okay. So no, sorry. So you see what I'm trying to do. I'm trying to get some intermediate map such that the final map is just plus. Sorry, just one second. Yeah. So can somebody help me over here? I'm like trying to really get it down to the least blocks that we have.
So are we looking for the map Px, Qy, RZ? And at the end, the
no. So what I'm just trying to look at this map x square plus yz, for instance.
Okay.
So how do I do this? By the way, this is completely pedantic. Okay, so if you feel that you don't need to see this feel free to leave, or feel free to leave for whatever matter after. So yeah, so what do I do here?
So in that case, do we want x square comma yz?
Right, but so okay, so here's the thing, what I'm trying to do. I am trying to reduce everything to the following maps, following identity map, projection maps, then addition map from R cross R to R, and multiplication map from R cross R to R. That's all. Okay. So here. Okay, so let's do this. So here is the map pi1 to R. Then it's the map from R to R cross R, which is identity comma identity. You see what I'm doing? So this is starting with x, y, z. Then the first map gives me x. Then it just duplicates it to x comma x. See, all of these maps are continuous because pi1 is continuous, identity is continuous, and in each slot I have a continuous map. So this is a continuous map. And from here, what do? I have multiplication. That is a sort of bizarre way of saying that the map that takes x, y, z to x square is a continuous map, broken down to my completely elementary units, the ones that I want to use, like a Lego box, the elementary connectors. So this is what I have gotten, x square. Then what do I have? The map from here to here, which is pi2 comma pi3, right? So that is a map from R cross S. That also is, sorry, 1 second. So let's not do this. Let's not go to the same R. Let's go to a different R. So this map to R is also continuous. That is giving me YZ from, and now this R cross R to R, there is the addition. That is also continuous. Pure bed entry. But I can get this, see, for polynomial maps, I can get everything down to these. Projection maps, identity maps, multiplication of real numbers, addition of real numbers, and subtraction, whatever. All polynomial maps are built out of these by and composition, of course. Composition is very important. So you see, the general matrix multiplication map is also exactly like this. Now, if you want to make a formal proof out of this using this method, it is going to be a bit unpleasant, you see, because some kind of induction and some kind of notational labor is required to write a general polynomial in terms of a coefficient that will have a multi-index, which is given by the powers of individual variables. So some unpleasantness is required if you want to write a formal proof showing that all polynomial maps are continuous. But anyway, I mean, I hope that this answers the question completely.
Yes, sir.
Okay, so anything else? Yeah, so so since I'm late from my side with homework, like the formal homework, let me tell you what I am attempting and what I would like you to do. Okay. The ideal thing that I would like you to be able to do is that if somebody said, okay, I have whatever, 3 hours, 4 hours, 5 hours, something like that, then I want you to be able to give the entire thread of the course from your side. The organization should come from your side. And that maybe is the hardest thing, that it's not that, okay, so you see the role is completely changed. You're not the student where somebody is asking you a question and you're trying to please them. As a teacher, if somebody says, hey, what is this course about? And so then you say, okay, these are the definitions. This is how the flow of logic is. and you sort of recreate the entire thing. Or if somebody says, okay, how about this particular theorem? How do you go up to that? Then can you start with original, elementary definitions that we began this course with, and find an efficient path from the basics right up to that result. So this is a difficult thing, but this is sort of the goal that I would like to suggest for you. And when we have an oral exam, then of course it will not be the entire course. I will not, of course, not ask you to explain the entire course, but I will try to get you to show your thinking in this direction. Okay, this is the concept. Where does it come from? What are the definitions? What are the results? And what is the flow of ideas? Sort of like, one analogy that I like to give is that if you go to a new city as a tourist versus if you are a resident of that city, then your knowledge of it is dramatically different. No? Where, so if you can two people may be able to get from one place to another in a city and do the exact same the exact same physical motions. But when a tourist does it by consulting the map at every corner and asking this person, that person, and maybe taking wrong turns, versus a person who is intimately familiar, like a taxi driver, for example, and can go from anywhere to anywhere by making continuous mental adjustments. That's sort of the difference. So when you're learning when you're learning some material, it is the latter that you want to work your way towards, where you have command of the material as opposed to fumbling through it. And in the oral exam, I will just try to see where your thinking is, how comfortable you are with the concepts, and how you can deal with them, how you can play with them and go from one place to another. Anyway, so are there any further questions?
So when are you assigning the assignments?
No, sorry, say that again.
Sir, this is regarding the assignments.
Right. So yeah, so sorry. So that was a long way of saying exactly what I want you to write. I will tell you. I mean, it's taking me time. But one thing I'll promise, that if I will give you enough advance notice. I'm not going to say this is the homework, submit in 2 days. No, that will not happen. And for the midterm exam also, you will have minimum 1 week where I will tell you exactly what is required. That is, this is a good set of problem. Okay, for the midterm, I should tell you that in a way I have already given you enough. That all the problems that I have given in class, you should be comfortable with all of them. If you are, and going down to definitions. Okay, so if you are asked to justify, well, why this step, why that step, and then if I say, okay, you say this theorem, that theorem, and I say, okay, why this theorem, why that theorem, that also you should be able to explain down to definitions. Okay, so if there is nothing else, then we will stop and we will continue on Wednesday.
Thank you, sir.
Okay.
Thank you, sir.